This time we're going to start looking at some real step responses of real circuits which are not immediately obvious to work out. But we'll start with some simple ones, just first order systems. That's systems with one pole in their frequency response. Now there are four different cases to consider. If you have one pole, then you can have a maximum of 1 0. But that 1 0 could either be at 0 Hz, or some finite frequency below the pole, or some finite frequency above the pole. In this video, I'll just consider the two simpler of these four cases, the first two. Now we've seen this circuit before in a different context, but the mathematics of working out the step response is exactly the same as the mathematics we've seen before. We just consider the current through this resistor here as being, let's say, I, and that means that the voltage across the capacitor, I'll call it X here, it's a function of time, is going to be given by I equals C dx dt. And that comes from differentiating the characteristic equation of a capacitor, that the excess charge on one plate is the capacitance times the d voltage difference across the capacitor. Also, we know that the current I is, by Ohm's law, going to be given by the voltage difference across the capacitor, which is A as a function of t minus X as a function of t, if A is the voltage at this point here, divided by the resistance R. And we can eliminate the current I between these two equations, and that would just give us that A of t minus X of t is equal to RC times dx dt. Now, for all times that we're interested in, A of t is going to be equal to 1. For negative times, A of t is equal to 0, but for negative times we already know that the voltage at the output is 0, there are no voltages or currents anywhere in the circuit. So we're just concerned with working out what's going to happen when A of t goes to 1 and stays at 1. So we can just simplify this to 1 minus X of t is RC dx of t dt, and therefore that dt over RC is dx over 1 minus X of t. And we need to integrate that up from 0 to some time t, from the initial value of X of t, which will be 0, up to the value of X of t at the time given by this t here. Integrating this term up is easy, that's just t over RC. Integrating this term up we can do by noting that the differential of the denominator is minus the numerator of this expression, and therefore the integral of this term has the form of minus the natural logarithm of 1 minus X of t. Evaluating that between 0 and x. That gives me minus t over RC equals the log of 1 minus X of t minus the log of, well, 1 minus 0 would be 1, but the log of 1 is 0, so in fact minus the log of 1 is 0, we can neglect it. Bit of rearranging on this, we get to the final answer. The output is 1 minus e to the power of minus t over RC. We've seen that before. We identified RC as being the time constant of this system. And it's exactly the same maths that we have to do here to work out the step response of this network. The other case to consider here is one that tends to confuse people a little bit more, but we can analyze it in exactly the same way. We'll start off with a voltage at that point in the circuit. That's our input step. It's going to be 0 for all negative times and 1 for all positive times. That goes through a capacitor, down through a resistor to ground, and it's the voltage across the resistor that I'm interested in, X of t. Once again, I can analyse this in terms of the currents flowing through the network. If the current there is I, then I know that I is C times the rate of change of the voltage across the capacitor. The voltage across the capacitor is A of t minus X of t dt, and the current is also equal to the voltage across the resistor divided by the value of the resistance, X of t over R. If I separate this terms here out, I would get C dA dt minus C times dx dt equals X of t over R. Now, for all times that we're interested in, A of t is a constant. It's just equal to 1. Therefore, the rate of change of A of t with time is 0, so I can neglect this term. That just leaves me here with something I can rearrange to dx over x is equal to minus dt over RC. And I have to do the integration again. Integrate from time 0 to time t from. Now, this is where the slight complication arises. What is the output voltage X of t at time t equals 0? And the answer isn't 0. Because when we're doing this analysis here, we're assuming that A of t is 1. It's constant. So we're actually analysing from the time just after time t equals 0, when A of t has already jumped up to 1. No current has had a chance to flow yet, so no charge has moved round the circuit, but A of t has just moved up to 1. Well, the voltage across the capacitor before the step arrived was 0. Therefore, the voltage across the capacitor just after the step has arrived must be 0 as well, because there hasn't been any time for any charge to move on or off the capacitor, so there hasn't been any time for the voltage across the capacitor to change. The voltage across the capacitor was 0, so it must still be 0 just after the step has arrived. The input has just jumped up to 1 volt, which means the output must have just jumped up to 1 volt as well. So that is a 1, the value of the output when time t equals 0. And that goes up to the output value at this particular time t here. Then it's just a case of doing that integral, log of x of t, evaluated from x of t to 1, equals minus t over RC. Once again, the log of 1 is 0, so that just gives us the log of x of t is minus t over RC, and therefore the output is e to the power of minus t over RC. And that's the result that we're looking for here. It looks like this. It starts at 1, just after time t equals 0, and goes on an exponential decay. But this is the point that often causes some confusion. You have to be very careful to get your limits of integration right. But just remember that you cannot change the voltage across a capacitor instantly, so just after a step arrives at the circuit, the voltage across all the capacitors must be 0. Similarly, you cannot change the current flowing through an inductor instantly. So just as there was no voltage on the capacitors before the step arrived, if there were any inductors in the circuit, there would be no current flowing through those inductors either just before the step, which means there will be no current flowing through those inductors just after the step either. As long as you remember those 2 points, you should be fine. Next time, I'm not going to immediately proceed with the other 2 first order cases, the ones where you have zeros not at 0. I'm going to take a quick diversion and introduce 2 very important results, the initial and the final value theorems, and they will greatly ease working out step responses in the future.